Hello everyone, this is Jeon Parjang. I am professor at 성균관 University. I will explain the overview of data structures. This chapter we have goals. The first of all, we want to distinguish between an array-based visualization and a linked list-based visualization. Secondly, distinguish between an array and a list. Thirdly, distinguish between an sorted list and a sorted list. Firstly, distinguish between the behavior of a stack and a queue. And then I will explain the concept of subprograms and parameters and distinguish between value and reference parameters. And also we will see the distinction between a binary tree and a binary search tree. After that, we'll see a binary search tree that is built from inserting a series of items. After that, we'll understand the difference between a tree and a graph. Finally, we'll see two search algorithms such as depth first search DFS and breadth first search BFS. So abstract data types. Abstract data type is a data type whose properties, that is data and operations, are specified independently of any particular implementation. So we can implement abstract data type using C, C++, Java, Python, something like that. Remember what the most powerful tool is for managing complexity. Application user level. We have three views of data. First one is application user level. This is the view of the data within a particular problem. And then view sees data objects in terms of properties and behaviors. The behaviors means the functions. Secondly, logical abstract level. This is the abstract view of the data and the set of operations to manipulate that data, okay? And then view sees data objects as groups of objects with similar properties and behaviors. Third one is implementation level. This is a specific representation of the structure that holds the data items and the coding of the operations in a programming language. This view sees the properties represented as a specific data fields and behaviors represented as methods or functions implemented in code. Describe a word processor from these three views, okay? The first one is application level, secondly, logical level, thirdly, implementation level. So composite data type, this is a data type in which a name is given to a collection of data values. Secondly, data structures. They are the implementation of a composite data fields in an abstract data type. Thirdly, containers. Objects' whole role is to hold and manipulate the other objects. We have two logical implementations of containers. The first one is array-based implementation. Secondly, linked list-based implementation. So the array-based one is objects in the container are kept in an array. On the other hand, linked list case, objects in the container are not kept physically together. each item tells you where to go to get the next one in the structure using pointer. Did you ever play treasure hunt, a game in which each clue tells you where to go to get the next clue? Lists. Think of a list as a container of items. Here are 4 logical operations that can be applied to list. First one is add item, remove item, get next item, more item. So this shows array-based implementation. Okay, so we have array. The C language case array first one index is 0, second one is 1, up to max length -1. Okay, so this is a list item, this is array. Okay, list based here linked list. So this one is a pointer, points the first list item, and then each one has a value and the pointer next pointer field, okay, is included. So we have this kind of linked list. So data structures for a list, the linked list types, we have 3: single linked list, double linked list, circular linked list. Operations of a linked list: insert, delete, search, and merge. So using linked list, we can implement abstract data types, stack and queue. Stack case operations are insert, delete, and look up, and the queue operations are enqueue, dequeue, and lookups. This is the algorithm for creating and print items in a list. Okay, so we have data, more data, read a value, and then insert my list, read value, and then reset my list. And then items in the list are, so from list we can get more item and then get next, okay, next item and the right next item value. So which implementation is good? So linked list case we can using node structure. So in this particular case we are using a C language. Okay, so node type is contents next. Or double linked list case, we can have 2 pointers, previous one and next one. Okay, so definitions of node structure in C case using type def struct, and we can structure type. This one is called node underscore type 1 underscore t. Double linked list case, okay. On the other hand, we have 2 pointer fields, next and previous, okay, using pointer type. So you can see struct underscore node type 2 underscore t. Okay, this one points the same node, and the content is integer variable, integer value. So using singular linked list case, initially without the header node case, the p is null value, null pointer, and we add a node, and then this value is 1, and then next fields okay, initialized with the null pointer, and then we add another one 2, and then previous one is pointed by this second node next field, and then delete the case, this node p next we can delete. Okay, so using C code case, okay, we create a node case. We are using a malloc function. Initially pointer is null, so size of this structure we can make a typecast, and then contents are set to 1, and the next value is the null, and then now p point the ptr, okay, node. So we create another node case, malloc, allocate the node value dynamically, and then the value 2 next, okay, pointers next, on is actually this one. After that, PTR next. Okay, this is a PTR point. Okay, next point P, and then P is set to PTR, and then now P points the new item, the head of a list. So if we delete P, next is actually this one. So free, this one, and then P next set to null point because we deleted this one. Okay, next item. So singular or linked list. Okay, so we can see. So if we have another pointer header node, okay, so the header node, this value points the number of list items. Initially, H and P is the same pointer value, okay, and then we make addition, and then head this node next pointer this first item. We add another one. We add this one. Remember, the P is a point at the end of list item. Okay, so delete the case. We delete this one. Okay, and then the head next the point P. Okay, and then we can link like this. So we can make a circular double linked list case with header node. Okay, initially header node next the previous point to itself. Okay, and then addition case here, and then this one point this header node, and then head next point of this added item, and then H is previous one point of this new node. Okay, so we try to make a circular linked list. So we make another one case also. Okay, 10. Okay, nodes next point the new node, this next point the H node, and then this new node 20 previous point this first item, and then the header nodes the previous point the new item. So we can make circular linked list, and then from H we can navigate like this. We can go back. Delete the case with delete, right? So we handle the pointers. Okay, so delete this one, this next point, this one, this previous point, this one. Okay, other point value is the same. So stacks and queues case using linked list stack. So linked stack. Okay, so top point the stack member repo last in. Okay, first out. Okay, so Q case P4 first in first out. Okay, so this top point latest added one. Okay, front case the oldest, this one is front. Okay, so oldest one, and then we near case we can add a new one. So when we delete the case, the front node is deleted first. So that's why LIFO, first in, first out. This one LIFO, last in, first out. Okay. So stack is an abstract data type in which accesses are made at one end, like top. Okay, here. So LIFO stands for last in, first out. The insert is called the push, and the delete is called the pop. So name 3 everyday structures that are stacks. Okay. Okay. The stack LIFO implementation. Stack can be implemented by singular linked list. Top is the pointer to the last in node. Stack operations include the push and pop. Push is insert, pop is delete. So in example here, empty stack, top, point null, and then push 10 first item, okay, point, and then push 20 second item pointed by top, and then pop the 20 last in, pop up, and then point the first item here. So we can using stack operation here. So more data will read and then push stack. Okay, we make a stack, and then stack is not empty. We can pop and then write down. Okay, so we can print out the first top one first. Okay, can you simulate this algorithm in C? The Q, on the other hand, this one is an abstract data type in which items are entered at the one end. This was near, and removed from the other end. This is the front. Okay, so FIFO stands for first in, first out, first inserted one. Okay, actually first out. No standard Q terminology. So in Q, enter and insert. Okay, for insertion operation. The DQ case also DQ, delete and remove for deletion operation. Name 3 everyday structures for queues. Okay, using queues. So ATM waiting list, or also the message delivery in a computer network. People, okay, router can handle first receive the message, deliver first. Okay, queue people implementation. Let's take a look at it. Queue can be implemented by circular double linked list. Front is the pointer to the first in node. Near is the pointer to the last in node. So queue operations include in queue and DQ. Okay, example here. Front and near point empty queue, and then first in Q10, so pointer front near point to the same item, and then so another one first. Okay, this one first in, the secondly in. DQ case. Okay, remember first one is deleted first. Okay. So this operation read the data, and then we can construct the queue. Okay, read the data one by one, and in queue, my abstract queue. And then second loop case, until the queue is empty. Okay, delete first one using the front pointer, so we can DQ and print out. Okay, so can you simulate this algorithm in C? So let's call level. The algorithm that uses the list does not need to know how it is implemented. We have written algorithms using a stack, a queue, and a list without ever knowing the internal workings of the operations on these containers. Okay? Okay, let's move on. Server program statement. So we can give a section of a code a name, use that name as a statement in another part of the program software program. So when the name is encountered, the processing or control in the other part of the program halts while the named code is executed. Remember? So what if the server program needs data from the calling unit? So remember, we have two terms, parameters and argument. Parameter is identifiers, list in parentheses within the sub program function declaration. Sometimes they are called formal parameters. On the other hand, argument, they are identifiers listed in parentheses on the sub program call, function call. They are called the actual parameter. Okay, so this one case declaration of definition of function, argument, the actual running function call. So we have two call methods. One is call by value, the other one is call by reference. Call by value case, value parameter used. This is a parameter that expects a copy of its argument to be passed by the calling unit. On the other hand, reference parameter is a parameter that expects the address of its argument to be passed by the calling unit. So let's take a look at example here. So calling unit, okay, so data is address 0002, value is 30. This second variable case, address is 0003, value is 40. And then swap, two value is a swap. Call by value case, actually this data is delivered, okay. On the other hand, the reference case, data 1 address, data 2 address, 002, 003, and the exchange, okay. So call by value case, actually, even though inside the data 1, data 2 value swap, it after the calling of this function swap, there is no change. But reference case using address, we can change, okay. This is very important. Let's move on. Insert list item sub program definition. So this is a set list of values. Okay, this one, last one to item, and the length case. So list length is list length plus 1. We increases. Okay, we can increase the value length. And the insert my list value. This is a calling statement. Okay, this is actually definition of sub program function. Okay, so which parameter must be by reference. Okay, let's move on. So now we'll see a more complex data structure tree. So structure such as lists, stacks, and queues are linear in nature. That is, only one relationship is being modeled. More complex relationships require more complex structures like a tree, graph. Can you name 3 more complex relationships? 3. Binary search tree or binary tree and graph. So this is a tree. Tree is a connected graph, but there is no cycle. A cyclic or a cyclic, okay, graph. Okay. So this is okay, root, and this is internal node. Okay, this is okay. Last one is external node, or called leaf. Leaves here. Okay, so depth is the root. Okay, level is called depth 0. Root child 3, 10, 4. Depth is 1. So, and also we have height. The height is the number edges from root to certain arbitrary internal or external node, right? For example, 12 case edge number is 1, 2. Okay, so this is height is 2. But this tree is the longest height is tree height 1, 2, 3, 4. Okay, that's why this tree height is 4. So binary tree T is a structure defined on a finite set of nodes that either contains no nodes called empty tree, or is composed of 3 disjoint sets of nodes, a root node. This is a root node. A binary tree called the left subtree. This is left subtree. This is a right subtree. This is root. This is left subtree, the right subtree of root. So the tree, this node point to the root node. Okay, so root node. This is children of root node. Okay, this is children of this. Okay, so 5, 6 is the grandchildren of root node 1. Okay, so the terminal node. This is called leaf node or leaves. So this node 4 case left child exists. Right hand side case there is no. So what is the unique path to the node containing 5, 9, 7, 5, 9? Okay, so 5 here, 7 here, and 9 like this. So in 3K there is no cycle. The path from source to destination is unique. So binary search tree is a special tree, okay, used as a searching structure such as dictionary and the priority queue. Okay, so binary search tree T has the following property where X is a node in T. So in that case, Y is a node in X's left subtree case. The condition is Y's key value is less than X key value. On the other hand, if Y is a node in X's right subnode, like this case, Y key is okay, L list X key value. Okay, so we have like this. Root is X, X, Y1. The value is Y1 value is less than equal to Y, XX root node. So binary search tree mode case, we can see user data left hand side, right hand side point to the root, okay, left subtree or child, and this one is right subtree, right child. And this figure here, this node point this root. Okay, each node is a root of a subtree made up of its left and right children. Okay, so this one left tree, left subtree, this right subtree. Also, this one is a left child, this is a right child. Okay, prove that this tree is a BST, binary search tree. Property is the left subtree value is okay, and most this one parent, right? So we can see this whole value less than this one. On the other hand, the right subtree is at least this root value left hand side. So this is satisfies the property of binary search tree. So trace the nodes passed as you search. 18, 8, 5, 4 is actually doesn't exist, and then 9 doesn't exist, and then 15 or this one. Okay, and what is special about where you are when you find the null? So this is there an item in binary search tree? Okay, tree. Okay, this is point the root of tree and the item we want to search. So tree is a null case, return first because there is no tree, empty tree. And earth case, item equals import tree. So tree is root, right? Node point. So return otherwise. Item is import tree. 3 point current node. Okay. So last case. Left subtree is searched. It is great. Okay, greater or equal case. Right subtree is okay checked. Okay. So we have 3 kinds of tree work: in order, pre-order, and post-order tree work. So in order tree work case print the key of the root of subtree between printing the keys in its left subtree and those its right subtree. Okay, so left subtree key value print out, and then this root node keys okay print out, and then right subtree key value is okay print out. Okay, pre-order tree case print the root first and then left subtree. After that each okay right subtree print. Post order tree case print root left subtree first, and then right subtree, finally the root in order. Okay, so in order tree work case, in order tree work x point the root of tree, so this is not nil, not null case. Okay, recursively we can define in order tree work x left, because remember left subtree print out first, and then this, okay, in the middle, okay, node, and then right subtree is print out. Okay, so the print, this is in between left subtree recursive call, this is right subtree recursive call. Okay, pre-order case print first, and then okay, pre-order left subtree of x3, and then right subtree, okay, print out. Post-order tree work case print is last. Post-order recursive function called left subtree is search first, and then right subtree, okay, this traverse, and then print out x value. So if we have this kinds of binary search tree, okay, so in order tree work, pre-order tree work, and the tree according to algorithm. So in other case, actually sorting, okay, non-decrementional order, pre-order case print. After that, print. This one print something. Post case, this one is print last one. Posterior go to left hand side, and then right hand print, and then in the middle print, and then this guy is and then this is print, and then print. Okay, and then go up, this is a print, and then go up this one, and then print. Okay, print, something like that. Okay, so binary search tree building case, what key sequence makes the above binary search tree? So hint, one of the three work algorithm so can be used. Okay, so answer, pre-order tree work is used. Okay, you can think of it. Okay, and the building binary search tree case, remember this is pre-order, right? So tree is null case, put item in tree first. Else case, tree is not null case. Okay, the item is less than, import tree case, insert left subtree. Otherwise, equal or greater case, this, okay, operator item equal to great case, right subtree is used to insert. So calling, once we constructed a binary search tree, this is a dictionary structure. Okay, so this value is splitting. Okay, so left subtree key value less than this one, right subtree is equal to or greater. Okay, so searching case, tree search algorithm, tree x and the key value k search. So minimum, maximum. So this left hand side, leftmost search, this is minimum, rightmost search is maximum. Okay, so tree search 9 cases. So 9 value is left hand side, 9 is 15. This last right, so search this one, and then 9 is greater this one, 9 greater this one, 13, 9 less here. Okay, that's why we can get in this sequence. Okay, this sequence used to search. So to the search algorithm case, x is a null tree or the value is the same, return immediately. Otherwise, k is less than x key is left subtree. X left subtree is searched. Otherwise, right subtree is searched. So iterative case, this is recursive function. This is a recursive function case. The function, the same function name given, the same function is called inside. It is a recursive, okay, function, a kind of mirroring function. So iterative tree search case, we can use the for or while loop, not nil until or while this is nil, this is k value not, and then we can search, right? This is k is x, okay, less, we can search x sub 3. So x left is changes the pointer value x. Otherwise, right sub 3 is used. X right is set. Okay, so this value is set to x pointer value. So we can repeat right. Once we can find, we can return x. So in the while a minimum case leftmost sub 3, maximum is rightmost sub 3. Okay, leftmost, this is the maximum rightmost. Okay, so we can implement the left, okay, is until left is nil. Okay, so we can traverse. Okay, so nil case left nil is this one is return. Right case rightmost, right is not nil. Okay, not nil, but this is nil case. Okay, rightmost, this is nil, this is this value is print. Okay, x. Okay, so finally we can reach graph. Okay, graph is data structure has consists of a set of nodes called the vertices and a set of edges that relate to the nodes to each other. So we have two kinds of graphs. First one is undirected graph. The second one is a directed graph. So undirected graph case, a graph in which the edges have no directions. On the other hand, edge has direction. So from one vertex called tail to another, the same vertex. So the another vertex called head. Okay, tail and head. So definition. Okay, so graph G consists of vertex set V and edge set E, and we have two types of graph. So vertex edge, there is no direction. Okay, however, this is a direction. So this arrow means head. This one is tail node. Okay, so this one is a kind of loop. Okay, tail and head the same. So we have application of undirected graph. So the June, Shara, something like that, relation, social network. Okay, and the directed case is the airport train. Okay, travel route from Austin, Dallas, and Washington. So in order to Atlanta from Austin, Austin and Houston, the Atlanta. Okay. Otherwise, Austin, Dallas, Denver, and Austin. Okay. So we can using this directory where we can figure out the shortest or the shortest the travel path. So on directed graph case, we can implement using array adjacent matrix. Okay, this is one. And then linked list case, we can use adjacent list. So this graph case, the first array pointer is 1, 2, 3, 4 case, the graph vertices. Okay, and then this one is a point neighbor. This is okay, starting node, tail. This is head. So neighbors. Okay, this is 1 tail. Neighbor is 2. Neighbor is 5. 2 and 5. 2 case neighbor is 1, 3, 4, 5. 1, 3, 4, 5. Okay, and so on. So adjacent metric case, row. Okay, and the column index is actual vertex ID. So 1 case, undirected case, we can say there is no row. Okay, so 0, there is no link. So 1, 2 has the link, and then this is boolean value is 1. 3 case no direct link, right? So in that case 1, 3, 0, 1, 4, 0, 1, 5 case H1. Okay, so diagonal is the loop. Undirected case there is no loop assumed, so diagonal is all zeros. Okay, so this is actually, you can see this one 1 2 2 1 symmetric. So using the row line, and then we can fold, right? So symmetric graph case, index I, index j, row and column is changed. Okay, a I j, a j I element the same. This is symmetric. Okay, graph matrix. So we can implement directed case also. 2 1 2 1 case 2 1 2 4. Okay, one case is only 5 here. Okay, previously you can see one is 2 and 3, no direction, but this case tail can go to head, just one. Okay, neighbor. Okay, so we can implement like this. Okay, so and then so we implement this in detail. V is okay, tail, W is head, and this is next node. Okay, so and then this was we can have the root. Okay, starting head node here. So and then the one case 2 and 5, right? And 2 and 5 we can make like this, a single linked list, and then this value actually the count the head node in terms of tail node 1. Okay, so 2 case 1 3 4 5 1 3 4 5, and then this edge value is set, and then this next point to next neighbor node. Okay, so the adjacent matrix case is symmetric, right? So 1 1 is cost 0. Okay, direct case edge value 1 2 case 10, 1 5 is 20, other 3 4 case infinite value. Okay, so weighted case. Okay, so here weight. Okay, so previous also linked this weight. Okay, okay, we can similarly. So on weighted graph case, just one case edge exists, 0 case no edge. Okay, so let G consider vertex set V and edge set E on a weighted graph. Well, vertex is U element of vertex set V, and edge is UV. U is tail, V is a head node. Okay, this is the edge. Okay, so adjacent matrix case, leader A and J. I is tail, low index. J is head. Okay, vertex ID. This one is head. I is tail, J is head. So if there is some edge, the value matrix is 1. Otherwise, there is no edge case. Otherwise, 0. So one on loop case, diagonal case, all 0. There is no edge. But 1 2 1 5 case, 1 2 5 edge. Okay, that's why Boolean value 1. Other itself 3 4 case. Okay, 0 1 3 4 case. There is no direct edges, so that's why 0 Boolean value. The weighted case, we can define, and then adjacent matrix case, if ij edges case, actual edge value, this one is used 2 and 5 case, 2 and 5 30. Okay, 2 1 10, 2 3 10, 2 4 15. Okay, so the typical example of a graph is a road network graph. So this is a road map from Yahoo, and then we can make road network graph intersection model. Okay, using vertex. Okay, like this P vertex. The edge using the road segment abstracted as edge like this. Okay, and then given a graph, directed graph, we can extract useful information from the graph, such as depth first search DFS algorithm and the breadth first search algorithm BFS. Okay, so this class I will explain. The first one is depth first search, and second one the breadth first search. Okay, So depth first search case, is there any path from source to destination? Breadth first search case, what is an optimal path from source to destination in terms of the number of hops? If the edge value has the actual travel time or distance case, we need to use the Dijkstra shortest path algorithm rather than BFS. So what is the shortest path from source to destination? I mentioned that Dijkstra's shortest path algorithm is used. This is not discussed in this class, and we'll see algorithm course. The first graph algorithm, depth first assorted DFS algorithm. Given a starting vertex called tail, called, okay, and the ending vertex, okay, this vertex. But here, the starting and the not direct, maybe multi-hop, okay, multiple edges are involved. So how can we find a path from start the vertex to end the vertex? Okay, so BFS algorithm sketch here set current vertex to the start vertex and goes to the deepest path connected to one branch of current vertex is running as far down the path. Next, take alternative choices at the other branches from current vertex. So note, BFS uses a stack for searching. So we are see source code, pseudocode here. Pseudocode is symbolic logical code rather than specific language like C, C++, Java, Python. So that first the search starting vertex and the vertex, right? So set found to push, okay, my stack starting vertex, okay, and then basically using stack while not empty, not found, so pop node, and then the temp vertex is okay, current popped one, okay, and equal and destination, write down, and then we can say true. Otherwise not visited, right? Write down temp vertex not this, okay, write down this one not visited yet. Visited one case we don't, okay, consider the check again. So push all visited vertices adjacent the temp vertices neighbors and then mark temp vertex as visited, okay. So using this while loop we can search that first, okay. So example case, Austin case, that first case, this Dallas and this one and this one, right? So this is stack, this the stack and stack, okay, this stack, okay. Eventually we can check, and then we can see neighbors is actually check, and this is neighbor check, and then the visited one write down visit, okay, and then we can go to deep first, okay. If we cannot find pop up, okay, and we can search the next one, okay. So let's take a look that first search sequence by stack, okay. So Dallas, okay, from Austin to Dallas, okay, and then Houston, next one, and then this one has okay, Atlanta, okay, and Washington. So first stack Austin contained, and then this is Dallas, Houston is okay, push Dallas and Houston, okay, destination actually Washington, okay, and then this is pop, okay, and then its neighbor Atlanta is pushed, okay, and then Atlanta pop up and then Washington pushed, okay. So eventually we can get Austin, Houston, Atlanta, Washington. We can get the path, okay. So track the parent nodes for transit path, okay, the reverse path, okay, we can calculate. Secondly, Brad's first search BFS algorithm. This one is quite useful, traverse all vertices in a graph, okay. So given a starting vertex called the start vertices vertex and the ending vertex. So can we find a fast from start vertex to end vertex with the fewest number of airline stops? So BFS algorithm sketch like this. Set current vertex to start vertex. Examines all of the vertices adjacent with the current vertex before looking at those adjacent with those adjacent to current vertex. Note, BFS uses a queue instead of a stack for searching. Okay, remember, okay, DFS used stack. So browser first search shortcode here, start source node and vertex destination. So set found to first and then in queue by queue the start vertex. Okay, and then okay, as long as queue is not empty, not destination found, so DQ first. DQ, remember the near. Okay, so this P4 is used, right? So the front one is first visit one is okay, take out DQ and then compare. The same case, okay, print out. So we found end vertex. Otherwise, 10 vertex not visited case, write down this one, and then all adjacent neighbors unvisited vertices in queue, and then mark 10 vertex visited. Okay, so we can repeat. Okay, this one, and then found, write down path has been printed. Otherwise, path does not exist from starter vertex to end vertex. So this is the same okay one. Now we are looking at the number of hops rather than actual value. The actual value case, the Dijkstra sorted path algorithm should be used. Okay. So how can I get from Austin to Washington in the fewest number of stops? So BFS by Q. So this is Austin, front and rear the same, and then here Dallas in Q, Houston in Q, and then so Dallas is DQ first, right? So and then Dallas is neighbor, Chicago and Denver is in Q, and then after that Houston, DQ and neighbor Atlanta. After that, Chicago, DQ, but Denver is already visited, right? Not INQ more. And then Denver is Atlanta. Atlanta is INQ, right? To Atlanta here. And then Atlanta. Take out and the neighbor, Washington, unvisited neighbor, Washington. Okay, Washington is found. Okay, so we can know the number. Okay, from here to here, Austin, Houston, Atlanta, and Washington. Okay, the number of edges, hops, this path is a sorted path. But we consider actual this value, Dijkstra sorted path algorithm should be used. Okay. So track the parent nodes for the transit path like this, reverse path. You can check. So brother first search algorithm. Okay, so we are using this the detailed pseudocode. Okay, and this one I will not go to detail, but you can take a look. This kind of directed graph. Okay, previous also directed graph, right? So each vertex we can initialize. Okay, so color is white, it's gray is okay. This is starting point, the destination, the infinite. This is the parent. Okay, the previous parent point for reverse path, and then Q is a priority. This is actually Q, and in Q at the starting point, and then DQ and the neighbor colored, right? So neighbor is colored, and then the distance is updated, right? This, and then in Q, unvisited one on Q, okay, and then we can each neighbor checked, okay, and then DQ. We repeat, and then here the U is DQ1 case, visited one is colored black. Okay, so this is a notation color state of vertex. White is not included and not visited. Gray is included, potentially visit. Black one is dequeued and visited. Little d is distance from start vertex S to destination transit. Intermediate one is v, the distance. This is a pi predecessor vertex pointer of vertex v toward the starting vertex x, and then using this one we can create actual sorted path in terms of the hops. So this is a queue operation. Start is 1 and 3. So you can check this operation. So the front, this one is front, and for front, for near, front near, this front near the same, and then empty. So 1 5 1 5 4 3 is the sequence. So conclusion. So we learned the following data structures for lists, such as array, linked list, stack, and queue. And then we see program statement. Remember, call by value and call by reference and parameter and argument. Data structure for complex relationships such as trees and graphs. In the next classes, we'll learn the detailed data structures, algorithms, and complexity analysis, such as linked list, queue, and stack. Complex data structures, including graph tree, priority queue, and heap, and simple algorithm searching and the sorting algorithms. Finally, we'll study time complexity analysis. That's all for today. If you have a question, please let me know. Thank you for your attention. Bye.